Hi, this is Miss Logan. Today I'll be talking about electric current and direct current circuits. So we'll be focusing on voltage and resistance. So to get started, electric current is the flow of electric charge from one place to another. So we can define this by our charge, which is Q, over a period of time. The unit we're using is coulombs per second, which we also call an amp. So a closed path through which charge can flow must return to its starting point. So this is called an electric circuit. So how are we going to actually get our electrons moving? Well, we need a battery. So the battery is going to create a potential difference between both of their terminals. So when we talk about terminals, we're talking about the positive and negative side. For instance, this causes the current to flow through a flashlight, similar to the way a person lifting water can flow through this paddle wheel. So potential difference. So if you look at this picture, this paddle wheel, so the person is putting water in this, and then that is causing this to move. So that's creating that potential difference. So a battery that is disconnected from any circuit still has an electric potential between the terminals, and this is called our EMF. So EMF is just an electric potential, but it is not actually a force. So if we wanted to figure this out, the amount of work it would take to move a charge, we would just take the total charge times the EMF. All right, so the direction of current flow from positive to negative, so our current is going around like this, was decided before it was realized that electrons are negatively charged. So the current flows around the circuit in the direction of positive charge would flow. However, electrons actually move the opposite way. However, this really doesn't matter. It's just something important that we should know. So the actual motion of electrons is quite slow. But the electrons spend most of the time bouncing around randomly and only have very small velocities component opposite the direction of the current. So if we look at an electron, it's actually moving in this pattern, so it's kind of moving crazy all around. And the electrical signal is the one that propagates much more quickly. All right, so here are some of the equations that are going to be really important to us and are also on your AP Physics equation sheet. So Ohm's law is one of our most important laws in circuits. So this is saying that our V, so our V is our volt, which is our voltage, we talked about that last chapter, is equal to I times R. So I is equal to our amps, which is also our current, and then R is equal to our resistance. And as we explore circuits, we'll kind of learn a little bit about more what these mean. This is only used for certain materials, so we're talking about materials in a circuit. All right, so if we solve for resistance, we'll find that R equals V over I. The unit for resistance we're going to use is this omega, which is called an ohm. So make sure, just to go through, we measure resistance in ohms, we measure voltage in volts, and we measure our current in A for amps. All right, so resistance in Ohm's law, so if two wires of the same length and diameter will have different resistance if they are made of different materials. That would kind of make sense. This property is called a resistivity. Kind of a crazy word to say, but what is this telling us? So R, big R is our resistance, equals our resistivity, which is our lowercase p here, is L over A. So L would have to be our length, and A would have to be our current. So here are just some examples of different materials and their resistivity. So we can see that things like that are insulators, so insulators are not good at conducting electricity, have really, really high resistance. However, things like lead and iron, really good conductors, have very low resistance. This would kind of make sense, right? If we're making wires or circuits, we need to use conductors. So the resistance of a material goes up as the temperature goes up due to different thermal effects. So this is how we use thermometers. So the resistivity decreases as the temperature decreases, but there are certain class of materials called superconductors in which the resistivity drops suddenly to 0 at a certain temperature. All right, so let's continue talking a little about energy and power in electric circuits. So we kind of defined with Ohm's law what resistance was and voltage and also current, but let's talk a little bit about energy and power. So remember this is our potential. So our potential energy of a circuit is our total charge times the voltage. Therefore, the power, if we think all the way back to one of our first units, is the total work or the potential over time. So if we sub that in, we're going to get Q times V over T. Another way that we can say this is P equals I times V. So basically, if we took the charge over time, and that gave us I, and I is our current. Power is still also found in watts. Okay, so in materials for which Ohm's law holds, the power can also be written, and we can just kind of plug these things in. So we have power equals I times V, and we talked about that in the last slide. And for V, we're going to plug in I times R, and that's from our Ohm's law. And that gives us I squared equals R. So this is another way that we can write our power. We can also do this the opposite way. So we can change I, and using Ohm's law, we can plug this in and get P equals V squared over R. So just a little bit of background knowledge about this. So when the electric company sends you a bill, your usage is quoted in kilowatts hours. So they're charging you for the energy used, and kilowatts hours are a measure of energy. So this is saying if you use 1,000 watts for 1 hour, that would be 3 times 10 to the 6th joules. So that's basically how we're getting our kilowatt hours. All right, so let's talk about our last topic that's really, really important to this unit. So we're talking about resistors. So resistors can be placed in either series or parallel. So in this example, in these two examples actually, this is in series. So if we think about series, everything is all connected, and all the resistors have the same flow of electrons going around. So both of these examples are of series. So if we need to find the total resistance, we basically add them together. So the R equivalent is equal to all of the resistors added all together. Still, we're measuring resistance in ohms. Now, our second situation is if we have this in series. So this is saying that our current is breaking off based on the resistors. And we'll play a little bit with this in class, but think about it. If I take out one of these resistors, will the other ones work? So this is compared here. This one is in series. So to find the equivalent resistance, we're using the inverse. So we're saying 1 over resistance equivalent equals 1 over R all the way. So for this one, we'll work a little bit in class of how we do the math for this. However, it's almost the same as series. However, we're using the inverse. All right, so we may do some more complicated problems. So if a circuit is more complex, start with a combination of resistors that are either purely in series or purely in parallel. So for instance, in this first problem A, I would figure out the resistance of these two together, and then figure out the resistance of the entire one in series. So first I'd figure out in parallel, and then in series. So just to summarize a few things, so electric current is the flow of electric charge. We're going to use ampere for this, and it's also I. So a battery is using chemical reactions between our terminals, so that's plus or minus. And the potential difference between a battery terminals is called the EMF, which is this little E symbol here. So we can figure out work by charge times EMF. All right, so Ohm's law is on our equation sheet. It's the most important. So we're saying voltage equals our resistance times our current. We can figure out the resistivity of an object by R equals the resistivity, that's right there, equals L over A. So remember, L is length and A is our amps, which is our current. Let's go over some more things. So if we need to find power, we can find it using one of these three equations here, which we got using Ohm's law. In series, we're using this resistance, so we're adding all our resistors together. Finally, if we have equivalent resistors in parallel, and that is written wrong here, we are using the inverses, and we'll go over that math a little bit more in class. And we don't have to worry about these rules. All right, so please make sure you press submit and you fill out the Google form.